So here we have, I have designed a new block diagram for the sensor for the OBC. You can see that we have an STM32F4 board here, the one that we are using for the onboard computer, STM32F401. And then we have the USB-C for debug. We have the remove before flight switch. Basically, that will be toggled before flight. We have the serial wire debug header pins for programming. We have the UART debug, RGB status LEDs, brownout detector for power coming from the EPS board. We have an external hardware watchdog. This will be useful because the MCU itself has an internal watchdog, so it's more reliable to use an external hardware watchdog based on like the research I've done so far. You can use both, it doesn't matter really, but let's have an external one. Then you have a power monitoring circuit for the power coming from the EPS board or the electronic power supply board. We have the board activation switch at this point, basically just to turn off on this specific OBC board. Now here we have another very important part, which is the memory storage and RTC. Flash memory, external flash memory, SPI. I'll use around 16 MB of it for storage of log files and such. We have EEPROM, basically to store configuration data. For example, setting bits and setting, things like voltage levels you should check, current levels you should check, etc. We have an RTC here for real-time clock to maintain clock count in case the board goes off. I mean, it's space, so anything is bound to happen. Then we have a MicroSD card for storing telemetry data, the data we collect from the satellite. So we are going to design this in EasyDA. So this is the schematic I have. If you look at this point here, I have arranged this project. I've rearranged it basically to be contained in one single project. Then I've added different boards. So we have the altitude determination and control unit, rather the sensor board. We have the EPS. We have the onboard computer. So right now, this is the onboard computer that is open. Now, let's look at the image real quick. Let's start with something like flash memory. Let's start with the flash memory. So this is STM32. Then the first thing we do obviously is to open the data sheet for that. So I think I have it. Here. I think I have it. Data sheets, STM32. Where is it? It's not here. Okay. You can also click this, click on properties and click on data sheet. Should open the data sheet online. It's taking too long, but let's just wait a little bit. Anyway, so as we wait that to open, the flash memory we are gonna use is a 16 MB one. So go to LCSC, search for Winboard. There are different manufacturers that do that, but I'll do Winboard 16 MB memory. remove this 16 MB. All right, so we have these memories here. This is W25 128. This is a part number. This is a part number, so click on this. So we can copy this part number, but before we do that, let's confirm the size. So this number right here, 128, is the megabits, the size of memory in megabits. Yeah, so if you go to megabits to megabytes converter to bytes, you can see this is 128 megabits. This is 16 megabytes of memory. So change this. Sorry. So the next thing you should check is whether the part is in stock, and you can see this is like 11,000, which is enough. So I'll copy this part number, copy that, CDA, Shift F, and paste that part number. So this is the memory right there. Place. So I'll place it right here. What we need next is the datasheet. So the datasheet is available. Okay, this is done opening, so I'll download it, but also keep this tab open for now. STM32 401 CCU6 datasheet, and then we save it right here, firmware datasheets, save. Okay, cool. Right, this is a flash memory datasheet. I want to see the reference design first. This is the pinout, VCC, power supply, ground clock, data output, data input. So this is an SPI, so it has miss on MOSI pins. Let's check the specs. This is basically for driver writing, SPI. Characteristics. Just want to show you something. This is a supply voltage relative to 4.6, so I can use 3.3 with that. Then okay, so no reference design, which is okay, but I can, let's just do this. Let's wire it first. So this is V3V3. This is 3V3. 3V3. And then this is ground. Right here is ground. I'll put it right here. Then we need a filter from 3V3 to ground. Basically a 100 NF capacitor. I can copy this and place it somewhere here. So this is 3V3. Pull it up. Connect this. To ground. All right. So clock is 0 clock. Clock right here. TI is data input. chip select is active low, so DO is data output, which is basically MISO. You have IO2. We have that. What I'll do is I'll label this as flash CS active low, so I just put a bar on top. And next thing is oops, okay, this is flash DO, this is flash IO2. Let me just pull this out here. This is flash DI, but instead of calling it that, it's data input, so small c. It's small c. Clock is a flash clock, or we can say it is SCK. That's SCK for serial clock, SPI clock. And then the other thing is here is a flash IO3. I'll pull a design I used on this in this memory from a previous design. The output is MISO. Slave output, master is slave out. Okay, I'll pull a previous design, so just a minute. There's some pins that are tied to VCC and to ground. Yeah, here it is. Open a new tab. This right here is the image. So this is from a previous project. This is 8 MB though. I mean 4 MB. So I'm supposed to tie IO2 and IO3 to VCC. IO2 and IO3 to VCC. Okay. IO2 and IO3 to VCC. So I can do this. And this is VCC. All right. So that's the flash memory. I put it down here. The next thing we have is the EEPROM, right? We have the EEPROM. So let's look for that chip, that IC. So EEPROM, let's say 64 KB. EEPROMs are normally small in size because they store very small size of files. So we have this is 8024 to 56 kilobits. So this is to 56 kilobits. You can convert this kilobits to bytes. Let's look for to byte. So 56 256. Let's say kilobytes. Yeah, this is 32 KB memory. Which is, I think should be enough for my case, but let's look for a larger one. This is $0.4. This is 0.9. The smallest 2 KB is $0.07. Okay, for now let's stay with that. So I'll copy this part number. First of all, open the datasheet, copy this part number, and then place it on EZDA. Place. So this is 3v3, obviously. So take 3v3. And ground. Ground is VSS. This is 3, 3. All right. Right, protect. We might need it. So I'll just find out all these pins. EEPROM from right protect. EEPROM right protect. Okay. Then we have these pins. We have SCL and SDA. That is I2C. So I won't need these. These are address. I believe these are our address pins because we are using I2C. So, but we're gonna check the datasheet for that. This is SCL, Alt N, SCL, and SDA. Cool. So let's check the address setting here. The datasheet is open. Where is it? Right here. Datasheet. Yeah, I2C. Okay, device address. You can see that device address. So let's look for that. Device addressing. Select one of the 8 possible slave address devices. So these are 3 bits, and we can have 2 to the power 3, which is 8 possible slave devices addresses. So if we set a certain address, another I2C device cannot use it. So these guys are giving us like a free leeway to set whatever address we want. So what I'll do, I'll connect these pins to ground like 000, so that we set it to that specific address. Okay. So what I prefer to do is when I set a device address on I2C, I like to type the address of that device below it so that I know the address quickly when I'm developing the firmware for it. So this is 0000, that's 0x00 device address. Okay. Let's be more specific. EEPROM. All right, cool. I think that part is done. All right, so the next thing is the RTC. So let's look for an RTC chip. RTC. And just search for chips here. If we had more time, we'd have time to go through different, ICs and check all of that. But I don't want this to be so long, so I'll go with the best device we find. This is PCF8563. This is DS3231 from Maxim, from XP. Just checking the manufacturer at this point. And the next thing I check is the price. This is $3 from analog devices. There's also I2C. Let me use this guy here, 0.5. It's cheap enough. 0.4, which manufacturer NXP. $0.4. That's cheap enough. Okay, they're in stock. All right, let me use this guy. All right, so copy this, open the datasheet, come back here, paste. Place. All right. SCL and SDA. First, I wrote these two. Let's place them right there. VSS is ground, so I'll ground it here. All right. Next thing is I think this is let's check the datasheet. RTC is applied by an external battery, so ideally you should have a coin cell somewhere. What's this? No, not this one. Datasheet is right here. Not this one. This is a watchdog timer. Where is that tab? Let me close this one. Open this. Yeah. Oops, Chinese. Right, let's check it out. This is in Chinese, or whatever language that is. I don't know. Let's look for some more chips. I don't want to waste my time doing translations for no reason. This is $0.5. This is 0.4. So there's a difference of $0.1. It's not gonna make a big difference, but let me check the data sheet and see whether it's compatible with the language. All right, cool. This is perfect. PCF8563. So I'm gonna use this guy. Just delete this and Shift F. Paste that. Place. All right, cool. We go back to the data sheet and 1 to 5 volts. Looking for the reference design pinout. Pinout is saying int is the interrupt output, which is okay. Supply voltage and C not connected. P3 and 10 doesn't have them actually. So we'll come to read this data sheet later when we are writing the firmware, but for now, ideally you want to spend a lot of time in the data sheet before you commit to a schematic, but you know. So this is the application diagram. Let's see. We have an oscillator here. At 2.768 kilohertz. To see is pulled high, obviously. VDD. Where is that VDD coming from? From the master. Let me check something. So this is not gonna do it for us because we refer to our previous project because it's not using a coin cell. It's not independent. I want an independent. RTC. This is PC 8563. PC 8563. For our reference design. Again, reference designs are some of the most important schematics you can have. Sometimes when you want to expedite your design, you have to refer to what other people have done and your own work, so that you don't waste a lot of time trying to come up with something that has already been done. Just a minute. All right. So what we need here is VDD. We need a clock for oscillation, and we need a power supply. The power supply should come from 3v3 supply. So I'll look for 32.768 kilohertz. This is 32.768 kilohertz crystal. Use this one right here. So copy this part number, Shift F, Control V, place this. Okay. So crystals are unpolarized, so this is in and out. You have to tie one of these to ground using a capacitor here. Basically, it's the clock, just like this one. So the clock again is determined by the internal capacitance of the the crystals. This is 12.5. So what I do is 12.5 minus 5 picofarads, then times 2. So 12.5 minus 5 is around 7.5. Times 2, that's around 14. 15. Solar uses a 15 picofarad capacitor. 15 PF C0805 capacitor. Okay. Let me pick this one. I'm trying to move as fast as I can here because it takes time to design these kind of things. This is these are two. Okay. Okay, delete that. Ground this. Okay. Cool. So we have that. We have interrupt pin here. Let's not connect this. And then we have VDD. So this is RTC net label. Replace 3v3 clock out. We don't need this clock out. So, but you can test this with a scope. So what I'll do, I'll place a test point right here, just to confirm. Okay, that's that. Then SCLSDA. I think that's this is okay. Right. Forget about the aesthetics at the moment. I'll come to rearrange these things later. Now, next thing is MicroSD. So MicroSD card, we need a socket for that. Let's look for a design that the normal Arduino modules or STM SD card modules schematic. I think I have it somewhere. Actually, I know I have it somewhere. SD card. Let me search for it. Basically, as an SD card module, any schematic has just a converter and some communication multiplexer of some sort. But let's look what we get. That is one of them. This is another one. So we have this kind of circuit supplied with 5 volts. When we drop it down to 3.3 volts, then from there we supply this. This is a 74 LV. This is some sort of a gate, something like that. 74 LVC 125. Buffer is a line driver buffer. Yeah. All right. So let's convert this to. This is a SD card module. 24 LVC 125 APW. This guy. Is that? No, it's not this one. This one. Yeah, this is a buffer transceiver. So I'll place this here. Control V, enter. Place. Place it right there. me remove this. No, let me. All right. Ground is ground, obviously. Then VCC is that schematic. Not this one. Schematic. That's right here. So this is receiving a 3.3 volt signal on pin 14 and only on pin 14. Then it's decoupled ground through a 100 NF capacitor. So 100 NF, we have plenty of those. Just copy this one, paste it right here. Then connect this VCC, and it'll take 3V3. Put it right there. I like to see it. I like to see this. So I'll connect a wire here. All right. Next thing is this schematic keeps on disappearing. Yeah. So we have the power handled 3V3 and ground. The next thing is the connector, but because this is a module, I'll just put this is SEK through a 3.3K to pin 2A. 3.3K SEK to pin 2A. Right. So pin 2A, this pin, I look for a 3.3K C0805 component size, 3.3K. 3.3K. We have it right there. Copy. Shift F. Paste. Place. I'll place it right there. And then this is going to connector. And this is SEK. This is SD SEK. Right. The next thing is MOSI pin 1A. MOSI pin 1A through a 3.3 also to this pin. So pin 1A, right? Yeah, pin 1A. Paste that. This is MOSI. This is SPI. They'll share the pins. We'll check the addressing of these things later, because not really addressing actually the addressing. When leave it is SPI, but master slave deals with chip select and clock. But yeah, we'll check the bus slave master connections. For now, let's just wire it out. MOSI is right here. Where's MISO? MISO is going to pin 4Y. That's the output actually. So slave out 4Y. Now resistor 4Y. This is MISO. Okay. MISO. The next thing is chip select is going to pin 3A through a 3.3K resistor. 3A chip select. 3A. 3A is right here. Copy this, place it right there. and then we name this net. So I'll move this a little bit, then move this a little bit right there. Control V, place it here. This SDCS active low CS active low. All right. Now these are coming from the master, the STM. Okay, mostly clock, MISO, and CS. Now we have to add a socket, but before we do that, there are some grounded pins. One output enable, I think is two output enable. They are tied to ground. So 2 OE and 1 OE are tied to ground. So I can just do this and that. And I think also these are the ones. 40E and 30E tied to ground too. Place that and place it right here. Okay, we'll come to clean up this later anyway. Okay, so then let's connect the SD card itself. So you need to look for an microSD card module. MicroSD card socket. These are different things. MicroSD. These are MicroSD themselves. What's the name? What name is given to that? Let me check. Let me check here. Part number. Okay, so I found one part number. Not in stock. No, they're in stock. Okay, so this is $1, 1.8 millimeter slot microSD. What if I search for MicroSD slot. So different. Okay, let's look for another one. Push, 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 push. Push. Okay, I think this is okay. They're in stock, and these are 1.68. This was 1.8 millimeters SD card. So when we are buying, we have to use the right one. This is 5296. This is 5262. Just bouncing. Should be good. Let me go with this 1.68 SD card module. Shift F. Place that. Let me place it right here. Right. So back again to our schematic, which says these are grounded. I assume yes, they are grounded. VDD is coming from this VCC, which is 3.3 volts. The first thing I do is obviously power it. So you have to power the SD card. This is 3V3. PSS is grounded, so that's that. But then next thing is chip select is coming from 3Y. 3 output is chip select. So right here, I'll put a net label that says I say this chip select, right? So I'll say slot SDSC SD slot CS. Okay, so V pin is that pin 2 is CS. Let me check the datasheet for this guy. As it opens, let me just label these other pins. 2Y, 3Y. So 2Y is going to SCK. 2Y is SCK. So there's 2Y is right here. I'll pull these guys a little bit further. And these ones too. And then I'll place this. This is SCK. SCK. Datasheet. There's a pin out. Pin out, pin out, pin out. Pin out. That one, that 3. Okay, let's look for another one that doesn't make us go through all this hassle. Okay, close this. Let me check this one out. Data sheet. Is the mechanical design diagram. Okay, let's place it and see whether it comes with like better naming. I think I just have to look for the right conversions of this CD, TMD, VTD, whatever the clock. Okay, clock is right here. Let's stick to this guy. Clock. And then we place, what is that? What is that? What is CMD? Let's check that out. Okay, so that too is unconnected. CMD is MOSI. CMD is MOSI. So SD slot MOSI. Okay. VDD clock is okay. That 0 is MISO. DO that 0. DO is MISO. So then that one is not connected. Okay. So that 2 we said chip select is that 3 CMD, this one. Okay, connect and connect. All right. That 0 is MISO. 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 This clock. What the fuck is slot? Slot. 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 So we have SK, we have CS, remaining in MOSI and MISO. So again, let's check out that reference diagram. Where is it? Not that one. This one. D0 is going to 4A. 4A is going to D0 through 3.3. D0 is data is that 0, if I'm not wrong. Is that 0 used? Yes, MISO 4A through just play this guy here. Delete that. Okay. We just rearrange this a little bit. So that 0 is MISO through 3.3 resistor, yeah. And I'll come to rearrange these things later. Right now I don't want them to waste time. Okay, slot MISO is set to that 0. The other thing remaining is MOSI. MOSI is CMD, and CMD is, which pin is that? CMD is pin 3. The remaining unconnected pin here is 1Y. So one output is going to data in, and data in is CMD pin. All right, no resistor, right? 1Y here, no resistor. So MISO, CK, MOSI. This one, 1Y. Right, cool. I think we have MicroSD card connector right here. So I'll just move it aside and place it right there. Okay. Oh, okay. That was long, but there we go. The last thing I want to design in this video is what's remaining. What's remaining on the, I think we have had out this part, yeah, memory, storage, and RTC. Let's add one more thing. The simplest thing I can add in this video without making it too long. I don't want it to pass the 1 hour or 1 hour 5 minutes. RGB status LEDs. Okay. RGB status LEDs. Let's do this. Then these other things we'll design them in the next video. So because they are RGB, we can use the WS LEDs. 5812. And then we connect them to this guy. So what I'll do, I'll first of all finish the SPI connection, which means I have to set up this STM32 and check out the pins that are used for that purpose. From where, let me check let me open the MX configuration tool for STM. Right. That is so slow. That was slow. That was very, very, very slow. It's not supposed to be that slow. But I think it's because I'm explaining as I design. And also I don't want to make, when you're designing, you want to make your mistakes. The mistake threshold must, as you design more circuits, your mistake threshold should go down. Like you should make less and less and less and less mistakes per design. Yeah, so I should update. What should I update? Nah. Okay, whatever, we'll do that next time. Let me add some RGBs and then we call it a day. We call it a video. Yeah. WS 458 12. Is that it? No, WS. What was the word? What was the name? RGB. WS LEDs. Addressable. 2812, not 5812. 2812. Yeah. These guys, they are good because the reason why I'm using them is because they are RGB first of all, so I don't need to use three different LEDs for three different colors. And also when I'll be writing the firmware, you'll see that when we need to show different states, we can show different colors. We can pulsate, we can blend colors, we can dim with PWM and stuff. So it's very easy and actually makes the cost of the whole device low. Yep. So I'm using like 3-in-1 LEDs. Copy this and place it. Place them right here. So I'll use 3. I'll use 4. I mean, for a satellite, the space is very small, so this is a luxury. Actually, I could have used just one, but because this is a technology demonstration kind of CubeSat DIY, I can, escape that. So ground, it's connected that way. And then okay, so remember these are addressable LEDs. So if you want to turn on one of them, you can just give them the address of that particular LED. You see they have data in and data out, right? So they are, it's like the LED strips. They are used in the LED strips, so they are connected in series, right? So what you do, this part you connect it to your STM board. So I'll call this debug and this, right? And then the data out comes to this. Data out comes here. Data out comes to the next. And data out comes to the next. This doesn't have to be connected. I can leave it unconnected. Then VDD can be 3.3 volts or 5 volts. But let's check the data sheet for that just to be sure. The last time I used them, they used 5 volts. Let's see. Five volts. They are always 5 volts. The other consideration you need to make here is on the power, because these are LEDs and they are current devices. I need to be sure that whatever that 5 volts is coming from, it has enough juice in terms of the current that it can supply. But we will do those checks as we move on. So I'll connect this to 5 volts and this guy right here, and do that and do that, because this guy is using, these LEDs are using the chip. We need to filter out need to filter this positive 5 volts. We need to filter the noise from this 5 volts. So what we do there, we use a 100 NF capacitors to filter that. So ideally, what you want to do is connect for each LED, you connect capacitor to ground. Right. Ground, ground, and ground. Okay, so okay, whatever. Yeah, let me let me place it at that point. That's enough. So the bag LEDs can come right over there. So this part will be connected to the STM MCU board. Okay, I think that's more than enough for today. Next time we'll finish the remaining parts, which is the USB-C, UART, SWD, these power detectors, and watchdog timers and stuff. Follow this diagram. Okay, have a good one.